You said you have a question about language models. You're going to come tomorrow to visitors, or you solved it?
We're good. You're very helpful. Thank you.
Oh, yeah?
Yeah, good to go.
You didn't do something for terms missing in documents?
You were right.
Okay.
Yeah.
So we said that a few times in class, and I'm happy to figure it out now, but just to recap the issue. In language models, homework 1, if a term does not appear in a document, so we have the score of a document is a sum of logs over all the terms of log of the probability of that term in the document, right? What happens when a term does not appear in my document? If I don't do nothing, doing nothing could mean many things. You had that problem before, right? Either I'm not including in my loop, or I'm not reading properly. Who knows? If I'm not doing nothing effectively, this accumulator over terms for that term will count as 0, because not doing nothing means adding a 0. This is for language models. For vector space models, the sum is typically, not always, say typically. There's some variations of it, but typically it's a sum of the same thing. W in here, of some score, like TF of W in the document, times something. Times additional stuff. The issue is this. If the term does not appear in the document, the TF will be 0. Multiplied by something will be 0. Therefore, not doing nothing, adding 0, is probably the default thing to do. But in language models, not doing nothing, 0. 0 is actually the maximum you can get into it. Because the log of probabilities is a negative. The maximum possible value is 0. That should correspond to when the term is actually appearing a lot. That will correspond to a very high probability, 0. Okay? So that was that. Let's see here. Where are we? So homeworks. You also said, are we trying to meet tomorrow? Is that it? Mm-hmm. 5:30 or so. I have to talk to these guys. I think one of them said they're definitely gonna come. So the meeting is likely to happen. 5:30. That means I'll show up at office hours around 6:30.
We also have a question that he has asked us to confirm with you. So one of our teammates he is document indexing all 20,000 documents, and then we are the other two partners are checking that if the link exists, is already indexed in our server, and then we are indexing it. If it exists, then we don't index it. We are not saving a copy of our documents on our local hard drive.
So you do that live at the time of crawling?
Yeah.
When you crawl, you send it to the index?
Yes.
Do you have the computers connected when you do the crawl?
Yes.
How?
We are using a library called Redis. It's basically a shared dictionary.
I see.
So we are checking it, we are uploading it on server, and then we are.
But what is the server?
Server is like Google, it's on Google. So it's Google server.
Okay, that's fine.
Yeah,
That's fine.
That's fine.
That's fine. Most people will find it hard to crawl live when they have already computers set up. If you do it with your local machines, how would you do this? You go to somebody's house, connect the computers, and start the crawlers. So people have done the crawlers separately and then do it. But if you have a server that's always on and you can save your team index in there, and everybody independently can do the checks. So what I want to prevent is you saying I'm the first, I don't have to do any checks, only you guys do checks.
Mm-hmm.
That's not allowed. So you cannot assume you're first. Everybody has to be an independent agent. Okay?
Yeah.
If you have this set up, that's fine. It's even better. It's more realistic that way.
Yeah.
But not everybody wants to set it up, in a cloud infrastructure. Sure, that's fine. And another thing that we said is you are required to make this check before writing in the index. Is the document in there and manage the links and all that. But if it's there, we're not going to check what policy you have. If you could say, like you did, if it's there, I'm not going to send it. You could say, if it's there, I'm gonna update it to whichever is more recent version. If I crawl later than my teammate, I'm gonna put mine instead of his. That's fine too. Any consistent policy will work. But you have to make a check. And you may have to update these incoming links. I mentioned this issue that if my teammate crawls a document and I'm pointing to that document, eventually we want to see that link showing up, even though neither me or my teammate alone can figure out the link, because we all have, I have the source document and he has the destination document. There's got to be a way to put a link back. So how do we do it homework 3?
Showed it to the TAs today.
Do we feel good about it? No good? Why not? We do trolling?
I did, yeah. I've never left Wikipedia.
What?
I didn't leave Wikipedia at all. I mean, I didn't do the entire 20,000 yet.
But is it taking a long time or?
Not really.
Okay. Did you do any merging? So who else? You guys did merging already?
Yes.
Who else did merging? Yeah, works. Like you tried it, it doesn't work? Not merging. Who else did merging? No merging yet? Okay. So crawling, it's a matter of mostly of time. Like once you set it up, you have to leave it running. You get 20,000 documents or so. Merging is more of a matter of software engineering. You're going to go back and forth with your teammates a while to see how that goes. All right, so Webgraph and Pagerank, that is homework 4. That's going to be 2 things, 2 graphs, one produced by you during the crawl and the merging, and the other one will just give you a link graph that we know the results for. Somebody asked on Piazza if we can post the toyish link graph. This is academic link graph, top 500 ranks. Yes, that's true. We can post it. So back to Pagerank. We had a graph last time here. It was 60. So I'm going to keep using this example for right now. What was it? A goes to B and C and F. And B goes to F and E. B and C. And C goes to E and B. D goes to C, A, F, and E. You don't have to write this, it's the same graph for last time. And E goes to A. I think we also added this in last time on loop to A. So this is of course a toyish example. We want to understand the better notion of what does people mean by a random walk. And we can also add probabilistic random walk. So there is, like I said last time, a lot of processes that can be modeled with a multitude of agents. So you can imagine these are restaurants or schools or places or web pages. And at moment t0, there is a distribution of agents on states. States meaning nodes. That is, I have n, say, equal 1 million agents, and I have few of them in each state at time t0. So I'm going to call that distribution. A distribution is, in plain English, a bunch of numbers that sum to 1, between 0 and 1. I'm simplifying mathematics here. Just imagine some set values that sum to 1, right? So I have, in my case, I have pi 0 at time 0. I'm going to say, here's A, B, C, D, E, and F. So what is the distribution at initially? I could start with any distribution I want. Typically it's uniform, but if I don't want a uniform, it doesn't have to be uniform. I could say, here's 1/4, 1/4, and maybe this is 1/8, 1/8, 1/8, 1/8. Is that correct? Some form? Say I can start with this one. Or it could be uniform. I can have 1/6, 1/6, 1/6, 1/6, 1/6, 1/6, or some other ones. Now, I think it's important at this point, unless you have a strong background in Markov chains and modelings for these processes. If you do statistics a lot, you're going to have to hit these kind of processes. But if you don't, here's how I think you should think about this. I remember what I did when in college I first time learned about it. I was in a math school, not in computer science school, so it's pure mathematics. It's easy to imagine a physical model. Rather than trying to deal with the statistics of it, which is math, imagine this being a physical model. And there's two models that correspond to this. They're equivalent mathematically. One is literally this. Think of this as being restaurants, and this being the Boston population. Today, everybody eats somewhere. Tomorrow, every single person would also eat somewhere. So at time t equal 1 or t equal t0 plus 1, every agent will move to a different restaurant in this graph. So that's a very physical model that says I have so many people, and we can replace restaurant with web pages, right? I say, where is everybody on the internet right now? What page are they reading? At time t. And at time t plus 1, I'm going to say everybody on the internet moved to a different page. Okay? The other model the other phenomenon that can be modeled this way is to say, it's only one agent, it's me, right? But instead of having, what will those numbers correspond to? Those counts of agents that are in a certain web page or restaurant. If it's only one person, me, I'm doing a random walk, this becomes a chance or probability for me to be in that state. So if I don't want to have 2 million people to deal with, I only have one person, I could pose the same exact problem by saying, what is the chance that tomorrow I'm going to have, I don't know, food at a certain restaurant? So those two models, so-called physical models, have the same statistical representation. Either it's one person and we're talking about the probability of visiting a page or eating at a certain place, or whether they're talking about 2 million population and we just count how many of those people eat at that restaurant. This is the same exact problem. Does it make sense? Yes? No? Okay. So I'm not very concerned in this class about the math. If we don't remember probabilities, it's not a big deal here, or linear algebra. But you have to create this model in your mind, not so much mathematical as rather physical. Okay, what is this about? What is this? We're talking about 1/6 or 1/8. What is 1/8? How do I think of this 1/8? And I should say this, there's no shame for a computer scientist to say, I'm not good at math. Most computer scientists are not, and they're very successful. It's good to be good at math, but if you feel like, okay, I'm not good at math, that's not a drawback. many people in computer science will tell you the opposite, will tell you that you have to absolutely be good at math. I don't think that's true to be successful. I think it's a skill, but there are many other skills that matter. And here it's not so much important to understand the theory. If you read the math paper, you see a lot of theorems. It's much more important to understand how does this particular model applies to my problem, in this case Pagerank or Webgraph. Mathematicians are much worse at computer science and modeling than computer science are at math. So you can feel good about that. You can say, buddy, you understand theorems, but you have no clue how this works with data, for example. Okay, so we have two models. For me, it's much easier to think this way. I have a large population, and this corresponds to counts. When I say 1/8, that's 1/8 of my population is in this node. Other people would find it easier to interpret as a probability. There's only me who's clicking the web pages or eating at restaurants, one person. 1/8 corresponds to the probability I have to eat in a certain place at a certain time. Okay. So what's a random walk? It's either all these agents, if I think of a population moving around, which is what actually happens in most of these models. We really have a lot of physical agents, whether it's people in restaurants or users on the web. We're talking about many, many people clicking on the web. If it's one agent, then it's what's the probability if I'm here to move to there. It's a conditional probability that says once I'm in this node D, what is the chance to move it in B? So there's a transition matrix, we talked about this last time, that says M, we can call it M, X, Y. What is the probability of moving from X to Y? And this is fixed. This doesn't change. And it's memoryless. In other words, the chance of moving from X to Y does not depend on anything other than being in X. So this is very typical for games. A lot of games, computer games and non-computer games like chess. The probability of winning or strategy of doing whatever or anything, they have all these statistics that are being computed and even machine learning implementations. All of these depends on the current state. It doesn't matter how the game got to that state. Once it's in a state, it's all from there. A lot of computer games work like that. It matters the current state. You guys know of any game that's not working like that? If I look at the board right now, or whatever I have, computer, display, it's not just the current state. There's other factors that affect the game. I'm not playing many games, so I don't know the answer to that question. But I know most games have this flavor of once I'm in a state that I can describe as the current state, it doesn't matter what was the previous state or the state before that. All my strategy or chances of winning or anything else depends on where are we right now. Most of those games have an open table, so to speak. You can see the current state displayed in full. Poker is not such a game, because at poker you always have the unknown variables. In chess there is no unknown variable. You see the board, it's what's on the board. Okay? So a lot of game implementations would rely on a model like this. We say I have states, and depending on what state I am, I need to figure out what of the valid possible states coming next, which one should I choose. So valid states will be indicated in here by what? What are the valid states? Once I'm in B, what are the valid states? Outgoing edges, that's a valid state, right? So if I implement chess for a certain state, the outgoing edges will be, these are your possibility for a move right now. Or I don't have to implement all possibilities. There will be maybe a pruning of only the possibilities that make at least some sense. What would be the problem implementing chess this way? Suppose I do this. And I have a graph with all the chess possibilities, and I draw the edges. It's quite easy between two chess possibilities to put an edge or not, because I know, is there a move, a chess move from B, some state, that will put me to E, it's a valid move. And if there is, then I have an arrow. I could get from this state to that state. Everybody's familiar with the game of chess? You don't have to know all the rules, just there's those pieces and there's legal moves, and you win in certain conditions when you attack the king and there's no way out, right? Suppose I do this. Suppose I write down all the chess possibilities and I put arrows between the valid ones. Then I need a machine learning algorithm. I don't want to go at random, even though from here I have 4 valid moves. I don't want to pick at random one of the 4, right? There's probably in chess often that one move is much better than the others. So either I implement algorithms based on chess knowledge. I'm a very good chess player, say, so I can decide for each state which way I want to go. Or I could let a machine learning algorithm to play a lot of chess games and figure out of these 4 possibilities from this state, this one is typically better. It can give me some probabilities too, right? This is typically a reinforcement learning type of process, that's how it's called, where I let the machine play all the possibilities until it figures out so many cases you win going this way, so many you win going this way, and so on and so forth. What would be the problem in doing so? You are now the software engineer. Why this is not feasible?
Just not the probability, you also have to check what are the opponent's positions.
You need to see if the opponent is playing optimally.
Right, but the machine, the computer learning algorithm, reinforcement learning, can play for 2 players, right? Can play for player A and for player B. For both of them, there is a exploration versus exploitation phenomena, right? I could pick something that worked before, but if I keep doing that, I never have the chance to check the other one. Or I can, typically reinforcement learning in the beginning prefers exploration to check out more links. Once it has some idea of how all the links work, it tends more to exploitation, which is let's use the ones that worked before better.
Wouldn't the problem be that you have so many states that you would have to play an intractable number of games?
Correct. How many states would that be in chess? 64 states?
No, very more. No, 61.
How many configurations of the chess board are there that are different and not equivalent to each other? Yeah, like, you know, there's a famous saying, I think in Egypt, there was a guy who invented chess, the king liked it so much. I forgot which king, but long time ago, right? He liked it so much, he said, this game is amazing, I'm the king of Egypt. I can give you anything you want back for this game. And the guy said something very simple, for each pawn give me 1 grain of, in Egypt they have a lot of wheat, right? So give me 1 grain of wheat, for the second one give me 2, for the third one give me 4, and so on and so forth. And the king said, oh, that's nothing. It's the only thing you asked, but that turned out to be like the whole wheat you know, product for like 10 years or something. Anyway, anecdotal things. How many states are in chess? 1 million? 1 billion? Few billions?
Million.
So this is the kind of problems that as computer scientists, you should have a way to solve, even approximately. You don't have to know the math, but if you go ahead and implement a program, say for chess, you're going to want to estimate in advance how many states we're talking about here. You could be wrong with that estimate a little bit. You don't have to know exact, but if you estimate it like this guy, the king, says, oh, that's nothing, no problem, I'm going to give you what you asked for, and then turns out to be way too much. You don't want to be in that possibility. The class that's typically called discrete mathematics for computer science help out with those things. You know, how many states we're talking about here? Too many. Can we solve it somehow? Like, what will be the solution? I still want to implement this kind of process for chess, but I can't have that many states. The solution is to group the states together, right? So is it possible to take a bunch of states in chess and make them one node? This now corresponds not to one particular configuration, but all configurations that have so many pawns advanced and the horse in that spot and the turn, you know, the one that goes on the line, anywhere on this line, and maybe string missing. Now, I just described 25 million states that have that characteristics, and I can say all of them are here in B. What would allow me to group the states in chess? When can I group those states to apply this kind of memoryless mechanism? If I put 25 million states right here, they have to have the same outputs. Right? Between now, I have so many states here, so many states here, so many states, so many states here. I have to be able to describe the edges, saying, if you move that horse from any one of these states, you end up in one of these states. That's not an easy thing to do, but that's how we can think about these games. Now, chess is a little bit difficult to implement that way, but things like a lot of card games could be implemented this way. Because, say, in poker, it doesn't matter which exact cards you have by colors, or whether it's you know, you have 3 kings and 2 eights. You can say that's almost the same as 3 kings and 2 sevens, because the kings are the dominant card poker-wise. So you just put all the 3 of the, you know, full hands that have 3 kings and 2 small cards in one set, and then you can do that. All right. So Markov chains will address the problem of, I want to measure this distribution with time. What happens when I move from time 0 to time 1 to time 2? How this distribution evolves? We already said last time that the actual distribution at time t plus 1, it's easy to compute. This would be, as a vector, it's going to be, what did you say, pi 0 times the m. So that's an equation that I think you really have to spend some time to understand it. This is a vector form. So this is vector matrix. This is 6 times 1, 1 times 6, 1 times 6, 6 times 6, to make the multiplication work out. And you really have to think, what does it mean in terms of a particular value? So if I am to say, okay, who is pi 1 of A? What this equation is saying, that's the sum over all states of pi 0 of that state times m is the probability of moving from x to a. That's what this equation as a vector says in terms of the actual values. And that is true. Why? Why I can measure the probability of time t plus 1. So day 2 or day 1 after day 0. I want to say the agents that are going to eat in restaurant A or click on page A could be obtained, the count could be obtained by this sum. This is saying, look for all the pages of restaurants you had before, see who was in there, how many people were there, and then multiply. If there were like 100 people on this page X, how many of those will move to A? That is this probability that says out of this 100, how many of them now will follow that link to move to A? So this equation, which is a linear algebra equation, corresponds to this, which is our modeling for how many people will move totally to A. That's how many people will move from A to A, from B to A, from C to A, D to A, and F to A, and so on and so forth. So you sum up those quantities because those users are distinct sets, right? The ones coming from B are different than the ones coming from C. Of course, some of these probabilities will be 0. For example, who cannot go to A? C to A will be 0, right? Because there is no edge. Okay, so I think that's what we talked about last time. One more thing, where do we get this matrix? In those models, you have to be fixed. You have to go to different models if you want the probability matrix, the transition matrix to change. For now, it's going to be fixed. but we gotta get it from somewhere, right? So if you play chess, you would use a reinforcement learning algorithm to get the transition matrix. What is the chance to moving from there to there? In here, we want to play any reinforcement learning. So I think, yeah, as far as PageRank goes, we're gonna assume uniform distribution. So we're gonna say, okay, if there's 4 edges, it's 1/4, 1/4, 1/4, 1/4. So we're gonna say, in effect, the mxy is what? The probability of moving from x to y is 1 over our degree of x. So that's saying if there are 4 links coming out of x, the probability to follow a particular one to y is 1 over how many there are. So in this case, we for anybody living B, because this 4 links is 1/4. For everybody living C, I think I missed a link here. Oh no, it's just E and D. That would be 2. C goes to D and so what's PageRank then? Of x is the importance of x as voted by incoming links. So it's a recursive definition. Says PageRank of x. Here's x. It's all kinds of pages coming in. So that's a V. It's the sum for all pages V of the PageRank of V. That's why it's recursive, because it depends on not only who votes for me, but how important are those that vote for me. Times, we say how much weightage is on a link. We're looking at this link that moves from V to X here. That's the probability of moving from V to X, which is the sum over V PageRank of V times, if we make this assumption of uniformity, that's 1 over our degree of V. But then we said, okay, that's fine, but we want to, every once in a while, jump around the graph. Now I'm moving into a graph where I can still eat at restaurants, and I'm saying I follow these links, but every once in a while, 15%, I'm going to jump around. So we're going to say that's 85% of these plus 15%, we're going to say jump randomly. Randomly, the chance of getting into X, it's 1 over the number of nodes. And I asked you guys last time, if I do this, this is the teleportation. Teleportation at random, 15%. And this part here is 85% follow link votes. Votes as in everybody who points to me, I count it as a measure of importance since that link points to me. Typically, when a page points to another page, it's like a reference, like I'm pointing the user to that place to read more about whatever is on my page. Can you think of anything else other than, so first of all, for restaurants, what are the links? If I'm back to restaurants problem, I have people eating at restaurants, what would be a link?
A person.
Hmm?
A person.
No. So agents in here can follow any link from D, right? D is a restaurant, C is another restaurant, B is another restaurant. Why would it be that somebody who eats in D will move to E, to F, to A, and to C, but not to B?
So they don't like county food.
Locations. Maybe people eat around their work, and then if you eat at those places, you're not gonna go across town. What else? Cuisine.
Yeah.
If I eat at a Indian place, maybe I won't eat at certain other restaurants.
Cost.
What?
Cost.
Cost. If I eat at cheap places, I'm unlikely to eat out of a certain fancy restaurant. Or in terms of everything that has to do with probabilities, you never want to say zero. Remember from language models, every time you talk about probabilities, avoid at all costs crystal zero. So when we model things like that, we never want to say never. There's always a small chance it probably is going to decrease. If we model restaurants, we're never going to say people who eat at cheap restaurants will never ever eat at a fancy restaurant. We'll say there's a very small probability. Same thing happens with web pages. If I Google and click on certain web pages, I'm unlikely to visit a certain page that has nothing to do with what I'm doing, right? What's another model that works like that really nice with nodes? I'm asking you, what can I apply this problem to? So I say restaurants, I say applies to web pages, games, states in the games, this will be the chess states, and the arrows will be the valid moves between them. But in terms of this navigational aspect, just like with web pages, it's a navigational aspect because once I visit a web page, those links tells me what else are you going to navigate to, right? So I found it that the restaurants example and the web page example are navigational in nature. It tells me once you see this, you're going to go see that. I found that the games, which can be modeled that way, are not navigational in nature. It has to do with the functionality of the game, much more to where the user is likely to go. That's why I think if you model restaurants or web pages, a uniform distribution over the outgoing edge, saying from here you can follow one of these four, makes some sense. But if you model a game, it makes no sense at all to follow a random legal move. Nobody in chess, even a bad player, will play a valid move at random and execute that move. Who's with me? I'm saying chess, but you can imagine many games in which playing random moves will definitely lose the game. But in terms of restaurants or web pages, once I have the links, it's not impossible for a user that, say, doesn't know much about diabetes, just landed on Wikipedia diabetes page, to click on a different link that I would click, or she would click, or he would click, because we don't know much about it, we're just exploring to see where everything goes. So in terms of navigation, people tend to follow more random links than in terms of, say, a game. What else? Is there any other thing that we can model with this that has a navigational aspect?
Like FIFA World Cup or T20 stuff, they're divided into groups.
So what are the nodes in FIFA World Cup?
The countries.
These are the countries. And once I see what is
The probability of that country playing the other country.
so okay, this is a country, this is say France, right? And what is the link? So E is another country.
Yeah.
What would be the link?
The probability of France playing versus the other country.
I don't think that models the FIFA tournament. I think we can think about it, but I think that as the tournament progresses, that probably will change, right?
Because first you're divided into groups, so you know the graph pretty well.
So the graph will have 32 teams, right?
Yeah.
But the problem is these probabilities will change as the tournament progresses. Right? Initially,
There might be new links.
I think we need a different model.
Pokemon Go.
Okay. What are the states?
So I think you have like certain Pokemon, and then if you get like more resources, you can get the next best one, or then you might want associated ones, depending on.
So what's an exact state? It's where I'm in the game, or I never played that, to my shame.
Yeah.
I've heard a lot about it. I even have some pajama pants with Pokemon on there. People make fun of me. No kidding. But I never played the game.
I think there's like a couple things going on. So you can upgrade, but then you might also want like players that are similar, or like Pokemon that are similar, depending on your strategy.
Yeah, but remember, for this model to work for any problem, including Pokemon, I have to have a state well defined, another state well defined, and the probability to move from this state to that state. You can define the states anywhere you want, upgrading, eating stuff, finding stuff, whatever. This probability has to be fixed.
Okay.
So if as the game progresses, FIFA World Cup or Pokemon, this changes. Initially I start to say the chance of moving from this state to this state is 20%, but later on is 40%. Then this model does not apply. There's got to be a fixed transition probability.
How about flights?
What?
Flights?
Flights is once I fly to Boston, I'm likely to fly to somewhere else, kind of thing.
Yeah.
Maybe, I don't know if those work like that. Somebody else mentioned this example last time, and I think the flights are organized now into these hubs. Like if you fly Delta, there's certain places you're gonna go to. So I think the model might work, but the states, doesn't make sense to organize the states all together, maybe. There's certain hubs and certain, like Boston, I don't think it's a hub, so, you know. How about reading academic papers? I'm sure you've seen some academic papers. Suppose those are the papers. What will be the links? Citations. Right. So those will be clear links written in the paper. Is it the case that somebody who reads this paper has a certain probability to read this other paper? Yes. Can I say that? Is that probability fixed? Sure. And does it make sense to make it uniform? In other words, if D has 1, 2, 3, 4 citations, should I assume a reader of this paper is equally likely to read one of those 4 citations? The model would apply either way. This is not a constraint on these models. You can have any probabilities we want as long as they are fixed. We said in the navigational problems like the Webgraph, we can start with a uniform probability and just move by that transition. Start with a uniform probability and assume a transition matrix that's uniform over the links. In citations, I don't think typically, I mean I'm sure because I know there's research being done on it, this is not uniform. You can easily see that if you look at the paper, out of the people who read that paper, or in general, the following of the citation is not at all uniform. If this paper has 4 citations, 1 of them or 2 of them are absolutely critical, most people read them, and the other 20 or so are not that much read. It has to do with several factors, one of them being the authors. People tend to read papers by authors that are more famous in every field. Another has to do with how relevant is this citation. While there are 4 citations, some of them might be directly linked to the paper I'm reading, D. You know how the author sometimes can say, we followed up the work of X and Y, and we based on the same model, and we just make a change. That's a strong citation because it means my paper is based on the other paper. Versus a weak citations, here are some other things that are similar, but we didn't look at them. Those are weak citation. It means I've heard of this, but I'm not really comparing with my own experiment in academic papers. So strong citations that tend to read a lot more. Also, Older papers tend to lead more. My paper from 2018 has citations to papers from 2017, 16, 15, and some citations from like 1975. Most users will find it easier. Earlier papers are easier to read. It's a known thing. So in that case, we shouldn't, if we use this for papers and citations, we shouldn't use uniform distributions. But these models can be used for that. How about for movies? If those are movies, what would be the links?
Actors? For genre?
The probability of watching that movie next. Is that uniform? If from here I can have probability to watch movies, do you think that's uniform?
It depends on the movie. They might
Let's assume that if I see this movie, I'm actually finished the movie. Like most sites, Amazon and Netflix and all that, will give you some options once you finish the movie, not in the middle of the movie. So let's say I finish the movie. I don't know if I like it or not, but then if I am to propose 6 movies, do you think it's a uniform probability from here to go to watch one of those 6? No. Very ununiform. Still very ununiform. Again, it depends on popularity of the actors. If I watch a movie with Brad Pitt, and one of these has Brad Pitt is big names in movies, right? This is much more likely to be watched than the other ones who don't have Brad Pitt, even though they're similar. Okay. So that's PageRank. Back to the problem we have. We can write this up still as a matrix multiplication. And there is a mathematical framework for finding a stationary distribution. So stationary distribution we call it pi star, is the limit when n goes to infinity of pi n, and must have the property pi star is pi star times m. In other words, once I reach the stationary distribution, if I move all agents according to the transition matrix M, I'm staying within the same distribution. So my probability got in an equilibrium point where if I keep multiplying, it doesn't change. Mathematically, this makes it easier to solve for pi star because it has to be an eigenvector for matrix M with an eigenvalue of 1. There's other methods to solve for pi star, but this will be the fastest one. Solve for the eigenvector with eigenvalue of 1, because this is actually pi star times 1 equal pi star times m. Again, no shame if we don't know how that works. You can go home and recap eigenvectors, eigenvalues to do this if you feel uncomfortable with it, but it won't be critical for this class to understand eigenvalues. We can just treat it as here's a math thing that there's a package that solves it for me. I just need to understand. I got a question. Give me a second. I much more care in this class about understanding you guys where this equation comes from. What does it mean, pi star to be equal to pi star times m? Why is this an equilibrium position? Why is this stationary? I care much less about, do you know how to solve it with eigenvectors? Because we computer scientists open up MATLAB called eigen something, and it's going to give me the correct answer, right? Even if I don't understand how eigenvectors work. I'm not saying you shouldn't understand. I think math is a good skill, but there's so many other good skills. So I think it's much more important here to understand the phenomena.
Do we always know that a stationary distribution exists on any?
No.
Okay.
There's some certain conditions of this graph that are rare, and it doesn't exist. So if you get a random graph, chances for stationary distributions are enormously high. But if you pick one by hand, we call periodic or erodicity. I'm not sure. I think it's something like that. Imagine I have something like this. The problem with this graph is that if I'm in here at time t equals 1, any other time after 1, I'll know exactly where I'm going to be. Right? Because at time 2, I'm going to be here, 3 here, 4 here, 5 here, 6, 7, 8, 9. So there's no randomness in this graph. The only thing is where you start. Once you start somewhere, you're very likely to, very sure you're going to be in one of these states after so many rounds. In this graph, there is randomness. Wherever you start, after 1,000,000 rounds, you could be in any one of those states. It turns out if there is a stationary distribution, it doesn't matter how you assign the first pi 0, the initial distribution of agents. Wherever you assign it, once you multiply with m many times, every multiplication with m would put me to the next round, right? You can think about it this way. Who is pi 1 as a vector? Is pi 0 times m. So the distribution next day is the original distributions times the transition matrix. Transition matrix is fixed. Doesn't change, remember? If we have to change the transition matrix for whatever reason, FIFA World Cup, things got eliminated, there's a higher chance now, then Markov chains don't apply. What happens after that? Pi 2 is pi 1 times m, which is who? Pi 0 times m squared. So who's going to be pi 20? That's going to be pi 0 times m to the 20. So every time I move to the next round, it's multiplying with this matrix m once. It turns out we can prove that unless we have very weird conditions, independent of how we start pi 0, this is going to be a stationary distribution convergence up to after so many rounds. Sometimes it converges faster, sometimes it takes many rounds to converge. And we have two ways to obtain the stationary distribution. We can solve this linear algebra equation with eigenvectors, and that will require decomposition of the matrix. MATLAB knows how to do that. Or we can do this many times until pi starts to not change that much. Same like with gradient descent or any other numerical function. If I measure the difference between pi 2 and pi 1, pi 20 and pi 19, pi 21 and pi 20, at some point it gets close enough to the stationary distribution that those differences are very small. When they're small enough, I could say stop, because you reach the stationary distribution. Now there's one more thing here. Is PageRank having the property of pi star or not? So if I look at PageRank formula, 85% times this plus 15 times that, is PageRank playing the role of pi star? Can I say, okay, I want to do this, but not for pi star. I want to do this for PageRank. I'm saying PageRank as a vector of all the nodes. So as a vector is a value for every single node in my graph. It's PageRank times some m, some stationary distribution. And then if PageRank corresponds to the stationary distribution, I can apply the Markov chain ideas to solve for PageRank, and I got the PageRank values. The answer is yes. This equation here corresponds to a linear algebra equation. So I can solve it by looking for the eigenvector of matrix M that has the eigenvalue of 1, or I can solve it by iterating over this, multiplying with M. M is the matrix I'm getting from this graph by assigning uniform probabilities, but you're going to have to change it a little bit to account for this 15%. I asked this in class last time. Did anybody figure out how to do that? In other words, without the 15%, M is, what is MFE? It's a matrix, right, of transitions. How much is MFE from F to E? 1/3, right? How much is MAB? 1/3. How much is MBA? That's 0, right? How much is MCE? 1/2. That's without the teleportation. It's just saying you want this formula 100% follow the links. But now that I add teleportation, so if I look at my matrix M, so I have A, B, C, D, E, F, A, B, C, D, E, F. And then what did we say? For C, I can go where? To E and to D. So for C, I have 1/2 and 1/2. For A, I can go where? I can go to itself 1/4, 1/4, 1/4, and what else? To F, 1/4. I get this matrix. That's without the 15%. What do I have to do to make it work with the 15%? If, again, what I'm saying is if I have 100% on this sum, to be exactly this, then I could say PageRank follows exactly the equation PageRank is equal PageRank times M. I need to make sure you guys understand this before I move on. Without the 15%, so let's imagine my equation is just this. Without the 85 by 100, just that. Can I say then PageRank as a vector is PageRank times M? With this equation here, means mathematically exactly the same as this. Right, it does. M being exactly this matrix of uniform our degree. Now I want to add the 15%. I want to say it's like that, but that's only 85% of the time. 15% of the time, I jump at random. I still want a linear algebra equation that looks like that. What do I have to do?
85%.
Change M, right? I have to edit M somehow. How? Is it, I think you're proposing M plus a diagonal matrix that is 15% of the diagonal, is that?
85% of this and 15% of this.
So 85% of this original M and 15% of the diagonal matrix I. 1, 1, 1, 1, 1 on diagonal. We know I, right? 1, 1, 1, 1, 1, 1, 0, 0. That is the identity matrix. He is saying, if you make your new M, take 85% of the old this M, the transition matrix, and add to it 15%, that's essentially 0.15 on each element, then this equation would hold, would be corresponding to 85% the transition and 15% teleporting. I don't want to say yes or no to that. I really want you guys to go home and figure out if this is true. Can I obtain this equation by doing that? I think you can, but I'm not sure that is the right way to modify M to make it a linear algebra equation. Once we have this form, we use the Markov chain solutions, either iterations or eigenvectors to get the PageRank balance. If that's part of your homework. Okay. Now, the moral of this lecture, which is mostly repeating what I've said last time, is not the PageRank. What I really want to imprint in here is that these Markov chain processes are quite useful in many situations. Seemingly unrelated. What has to do movie recommendations with games, with citations, and with restaurants? Every time, that's the way you have to think. Every time you want to model, and you're going to have to model a lot of things because every problem nowadays corresponds to something that it's modeling. It's impossible to solve a problem without modeling, just too much data. So you're going to need a model. Whether it's an airplane, a game, a production line, I don't know, ticketing, something. Every time this probability stays fixed, you can easily define a state. Say, I can say, here's a passenger that has certain problems, and here's the next state, police gets called. Every time you get clear states that make sense, and the probability between them is fixed. Can be anything as long as it's fixed. This is the way to go. Every time you say, okay, I'm on a mountain skiing, that's one state. The next state is something happens. If that probability stays constant, then this is a good way to go. if probability changes, then that's not the way to go. That's the characterization of this mechanism. And you might have heard of something similar. I don't want to go into it. If you study theory of computation, either as an undergrad or grad students, these automatas and how languages work. And they don't work like that Markov chains, but the structure is very similar, how to create a language based on these automatas with states and transitions between them. Okay. Now that's PageRank. And this is obviously based on just links. The values coming out of PageRank have nothing to do with the content of the page. It's the opposite of what you've done in homework 1 and 2, right? Homework 1 and 2, it's all about the words in the page, and the counts, and the TFs, and the language probability, so on and so forth. All this, the way you rank pages, have to do with, do those pages have to do with my query? Do they contain the query words? How often? Bigrams, so on and so forth. This has nothing to do with query words. This is purely a function of linkage. We didn't look at the content of this page at all. We just measured the links. So the difference between this and the first homework models is this is not related to the query and keywords. It's related to the links structure. And as a consequence of that, it's not a query return. PageRank values are global. They don't depend on the query. You can compute this, pre-compute this, right, in advance. And then PageRank is a static number now. As long as the link structure doesn't change, user queries and indexing does not affect PageRank values. It's a static value. So PageRank is static. Can be pre-computed. No keyword impact. Purely a function of links. Okay. So how about, so people immediately have asked, okay, that's good, that works somewhat. It has to be combined though with user queries, right? I mean, what you could do if you want to go back to a homework 1 model is, obviously, if you want to take into consideration web links, you could do something like PageRank, but you don't want to avoid completing people's keywords, right? If somebody asks for a nuclear bomb, I have to return pages that have to do with nuclear bombs, whether they have a high PageRank or low PageRank. I could go by a mixed course to say, okay, I'm going to look at all the pages that have nuclear bombs in them, and within those pages, I'm going to sort them by PageRank. Because if they have the same BF25 scores or similar BF25 scores, I would prefer returning high PageRank pages, presumably more popular, as opposed to low PageRank. So people have come up with something called topic sensitive PageRank.
If it was solely based on PageRank, how were they listing for?
If I only do PageRank, there is no query information. PageRank is a global score. So I can sort the pages by PageRank. The first one will be google.com. Second one will be amazon.com, facebook.com. And at some point, I think Google even published the PageRank values. I think there was a browser plugin or something. Even now, I think there is, that you could, in your return list, you can have the PageRank values.
So irrespective of anything, whatever you search, you get the same.
Because it's based on links, not based on keywords. Now, if I change the links, I will change the PageRank. By the way, how can I get a high PageRank? I'm the god of the internet. I created my own page, virtual.com, and I want to give it a high PageRank. What do I have to do?
Create more pages and point to your page.
Yeah, but those, let's look at the formula. So that's a good idea. The problem is the pages I'm creating, we're going to have a PageRank of 0. Right? So if I create a lot of links and put all those links to my page, I could easily work on this term here, because all these million pages that I'm creating, If I create only one link out of them, 1 over the out degree is a very high number. But I can't easily fool this value. All those pages created have a low page rank. So they're not going to result in a big page rank.
Randomness helps, and then push the page up.
The randomness from the 50%, you think if I jump at random, I'm going to find Virgil.com?
And in the next iteration, maybe the probability increases. I mean, instead of 0, it's like a little more, so it keeps increasing.
No, I mean really practical. Suppose we're bad people. You really, I really want to increase Virgil.com. What do I do?
You can link some of your new pages to each other.
Yeah, but initially they all have, that's what she said, right? I can do that. I can create a lot of pages with links to Virgil.com, but they all have a 0.
But I'm saying they also have links to each other as well.
Okay, so I have to,
Like more legitimate sites.
right, I have to wait for Google to kind of start parsing my subgraph there, and once it parses, it may be, Google now knows, by the way, about those link farms, so we cannot trick him with that, but a few years ago they didn't know. What would be a faster way to increase my page? By the same idea.
Maybe put like a comment on Facebook or something.
If I go to pages that already have a decent page rank, it doesn't have to be big. It can be small, but it's not 0. I find a lot of those pages that allows me to edit stuff. Wikipedia, comments, blogs, all the newspaper articles have a user comments things. YouTube videos have a user comment things, right? Those don't have page rank equals 0 because I can go to Shakira videos, and Shakira is a popular artist, so she has, that page has more than a 0 page rank for sure. Anything I type in there as a link has the property that the page rank of that page is not small. Maybe I can even find some popular blogs that allow comments that have quite a high page rank value, right? You know, anantech.com and some very respected websites that I can find. The problem is, if we all go to these pages, anantech.com has a high page rank value, allow me to put a comment. I put a comment that puts a link to virgil.com, right? We all do that. This term is still the page rank value of anantech.com as long as Google keeps it. But what happens with this term? If we all go to that page and put a link to our own page, the out degree will become very big, so 1 over the out degree will become very small. So that's what people have done, a lot of those things you can see. These are early strategies. Towards the end of the course, we're going to have a lecture about, okay, how can you abuse all those systems? And now it's much harder than before. It's still a chicken and egg problem. The more hackers come up with ideas for how to increase page rank or sell you ads or other things, the more Amazon and Google and the IT companies are, clearing up on those mechanisms, and they have a lot of machine learning filters in place. But that's the idea. Okay, so now we want to adjust this a little bit. We want to say, I want a few PageRank scores. So I want PageRank to be of a page like before, but on a particular topic K. So this is the importance of page X on topic K. The simplest version of this would be K is one of sports, business, entertainment, politics. We call this in data global tags. Like we think there's some sort of general categories that apply to mostly everything. And if you are newspaper or a broadcasting like CNN.com, you have some structure at the very top of hierarchy. Every article has some name tag. This is about politics, or it's in the politics section. There's the other tags that are much more specific and dynamic. This document is about I don't know, some particular issue or name or location. Those are not global tags. Global tags would be grant categories. So the easiest version of this is I have some few grant categories that are static. Okay, so first of all, what's the advantage of having this? If I manage to compute these values, PageRank, but not global page, I mean, still global, it still does not depend on a query, but it's not one value. A page X, you can think of it of PageRank of X on some category, K1, then we have PageRank of another category, K2, so on and so forth. If I have any categories, I have a PageRank value for each one of them. So the advantage is now that I can distinguish between pages important for politics versus pages important for sports. I still have a global hierarchy. It's just ranking is more appropriate for my categories. And you can set up those categories the way you want, but the more you have, the harder it's going to get if you make this list big. So if I have this, can I do something now for a query? As I said, the only thing I can do for a query with global static PageRank, one value, is to apply a model like a content model like we have in homework 1, BM25, and then say, within the same score of BM25, if I get a range of all the documents that have the BM25 score or the language model score, approximately that bucket, that value, resort those by PageRank. So within the same score of content, I would prefer showing high PageRanks documents first. Makes sense, right? If few things have the same BM25 score, I mean they have the same amount of keywords, I would rather put first the page with a high PageRank by release. That's a very crude combination of PageRank with the content. There's some other better mechanisms. Now I can do something better here. If I have a PageRank for a bunch of topics, how should I now adjust a query score based on this? So I would like to compute a page rank for a query on a page X. The model that we're gonna look for here is to sum over all these categories of the probability of that category given the query times the page rank in that category for the page. So we have this. This is pre-computed. This is the page rank of every page on a category, like sports and politics and all that. It's pre-computed just like we have the initial page rank. In order to do this, though, I have to figure this out. What is this? How do I know how much a category applies to a query? How do I do that? If I get a query from the user, this is given. How do I know is it sports or business or entertainment?
Use some sort of statistical classifier.
I can do a classifier, but I can just invent some heuristic rules, right? The following words in the query corresponds to sports. I'll have a list of keywords that says, if I see LeBron James, if I see any sports team, if I see anything like that, that's sports. If I see, political names like Donald Trump and, Sanders and all these guys, that's politics, right? People have tried heuristics. Heuristics work quite good, but not as good as machine learning classifiers. If you want to do this optimally, you typically implement a machine learning strategy there. Okay? It's not that hard for global categories. It's quite easy to tell, right? What are the words in a page that corresponds to sports? It's a short list, right? When this becomes dense, like many categories, like we crawl the Guardian set of about 500,000 pages from Guardian, and we look at the tags Guardian, the newspaper, puts on their articles. And there's like 30,000 possible tags. Now, it's still better than 500,000 pages, right? I mean, we're not saying every page has unique tags. That's not true. There's quite a lot of pages that have tags like science or UK healthcare, for example. That's a big topic in England right now. Guardian is a newspaper in England, right? So we do have enough pages per tag. It's still a lot of tags. If I have 30,000 tags, managing properly all these probabilities. This is not a 1-0 black and white thing. It's not like we're asking here for either on or off. We're trying to get the probability. Much harder to do 30,000 tags than a few grand tags. But that's how people have thought about this. And if you do data mining, this relates to something we studied there, and we're going to have a homework about it in here too. Relates to what? So this issue in here, I mean this sort of expectation-like formula appear in a lot of places before topic modeling. In here it's true too. Pagerank, topic-sensitive Pagerank took off before topic modeling became quite popular and straightforward. So this is an expectation-like formula. It's a value times probability of that value. But it's really for text and topic modeling that solve these kind of problems much better than PageRank or other alternatives. So the biggest thing with all these issues, topic modeling or topic-sensitive PageRank or concepts extraction, is how do you define the concepts? Are you getting this from data, or you have a predefined list of concepts or topics? And if it's predefined, is it big, is it small, how much data you have? In principle, all these models could do quite well if there's not that many topics and there's enough data for those. Okay. So we can take a break now, and then I'll talk about something else after the break, not PageRank. So I have here one more formula that is not related to this PageRank. I'm pretty sure you know what it is. It says probability of k given the query could be, it's approximately proportional to probability of the topic times the probability of the query given topic. We all know this formula, right? This is not related to PageRank. It's base formula without the denominator. But why is this useful? It's saying you want to estimate this? Here's what you can do. You can establish a prior, let's say prior, for each one of the categories. Priors could be estimated for much larger data sets, for example. And then instead of estimating the probability of a topic given the query, I could estimate the probability of a query given the topic. This may seem hard, but a lot of the caches that, say, Google has are organized that way. For a given particular topic or tag, how many queries I've seen, or what are the queries that I've seen for that topic. So it may be something that I keep track on anyway as a search engine. So then I could estimate data from there. Okay, let's take a 5 minutes, 10 minutes break. I still can figure out this link to track you out. Most of the website works fine, ccs.nu.edu. Yeah, but there's some link to this track eval, which is a Perl script, where I tried to make it a zip file. For some reason, it gets redirected to what, ccis.northeastern.edu. I don't understand why. I mean, how these redirects work?
There will be a DNS server.
But it clearly does not apply all the time. Like I'm redirecting to another link on the website here, it's a PDF. This PDF doesn't get redirected. It stays at ccs.nu.edu, but that track eval always gets redirected to. The ccis.northeastern is a new thing. It's the first year when it happened, so I don't understand. Why is the redirect based on some sort of analysis of the file? If they think it's a runnable script, it gets redirected. If it's just a regular page, stays there. I don't understand.
Does it happen for all the Perl? Does it happen for all the Perl files?
I only have that one. I could try put another profile there, see what happens. Sure.
And probably change the file name. That needs to be.
Track eval is not a problem. .pl might be. Maybe if I put .txt, maybe that works. Sure. And I asked, but I think they're doing the transition. They still have both available. So even the IT group, it's not. I don't think they know what's going on.
It looks like somebody wrote a dissertation on the 15% thing in like 2009.
Why is 15% or?
Well, it looks like I mean, it's a dissertation. I'm not gonna get it, but it looks like they're complaining that the 15% makes a single surfer and it kind of messes it up, and so they wanted to break out so you could have multiple surfers instead of just one.
And with different rates, you mean? The 15% is different for the surfers?
Random alpha Pagerank.
Okay. So there are many variations of it. I think you mean one that says some surfers have a 50% teleportation chance and some others have a higher chance.
Yeah.
I'm aware of, I don't know the name, alpha Pagerank, but I'm aware of people who did user studies a lot. So they're trying to map a user into a profile that has to do many parameters, one of them being what's the chance of moving randomly. It turns out that some people move much more random than others. You know, if you're like me, I never go to browse the internet with no purpose. Like I'm looking for something when I'm browsing, so I'm much more likely to follow links. But there are people who just do the internet like they do shopping, you know, they just go to the mall to see what's up. And then those people will jump much more, I guess.
Yeah.
I don't know. Yeah, so I think if you want to go into this, you can go into user studies. Big companies have much better user studies than academic groups because they have a large user base that naturally clicks something and naturally gives them feedback, and also have a lot of money that they can pay, you know, for the studies. But many people in academia have tried user study modeling, things like clicking behavior. They look at not just the links. See, those probabilities for transitions only look like at the links, right? In practice, people are more likely to follow links depending on things like how long is the document. A link at the bottom may be less clicked just because the document is so long. Very few people reach the bottom, so it's unlikely to be 1 over how many links are in there because it's a bottom link. Others have to do with menus, ads versus actual content. Very likely people click on ads and menus. Much more likely is to click on a link that's embedded in content. most of them are also based on relevance, like we mentioned this for anchor text. If the anchor text is related to my interest, I'm much more likely to click on that link than if there's any other link, right? So I think user studies is the place to go to understand those things. So anybody looked at homework 4? I think somebody was asking something with well, somebody was asking what are the PageRank values for the top 500 URLs in the other set, not the cold one. I guess that person is not here. I feel so good. Hey, somebody's at homework 4, right? So what's gonna happen is you guys finishing up homework 3 this week, homework 4 next week, probably. Then you have a big chunk of homework 5, which is evaluation, which includes annotations that you have to create. And then we're not gonna have that much time to do LDA, this topic. LDA does topic modeling and machine learning. So we'll see how much can we pack of homework 6 and 7. 8 is probably gone. No?
No.
Yeah, 8 is gone.
Yeah.
But we'll do 6 and 7 in one. I'll take 6 and 7, concatenate them, and say, hey, we only have 6 homeworks. Right? Feels better. You don't have 7, you have 6, but it's the same exact exercises. Another thing, anybody has merging issues like connectivity issues? You say you find a library that allows you to do this. Is it free?
Yeah, it's a Python library.
Okay, so, because we have a router, I don't know if the TA set it up, but I told them to set it up, just in case some of you have the difficulty of how to set it up. If you go through that router, there will be no difficulty, it's a private network. But by now, I think the issue has been solved somehow. I mean, most people, I remember last year, had no connectivity problems. Okay, so we're gonna go for about an hour and a little bit into more research mode, okay? A little bit beyond the basics of Webgraph. Let's see how far can we get in there. I wanna do this, but maybe better than just, this requires me to set up these categories, compute independent page ranks, and then queries get evaluated based on the page rank for categories and how likely category relates to a query, right? So to start, what do you think HIT stands for? H-I-T-S. Here. Hyperlink induced topic search. as you can tell, this is some attempt to do better than topic sensitive PageRank. It's topic search that sounds like topic sensitive, and it's hyperlinked, so it's based on links, just like PageRank. How about salsa? What do you think this stands for? Food? Or dance? Right? Salsa music? Or not in this case. This is stochastic approach for link structure analysis. People try to give fancy names to their stuff, so that's what happened here. They're not that fancy. Okay, so here's what we're gonna do. We're gonna discuss the basics of this stuff on the board, and then I'm gonna put the paper up on the projector, and we'll together go to the paper and identify key points on it. And then I'd like you to go home and try to read the whole paper and go over the parts that we didn't talk about. You're gonna see there things like mean average precision, which is the same number you read strictly value in homework 1, that value that you're supposed to get to at least 1.5. If you want to know what that means exactly, you have to wait until next week when I'm going to talk about mean average precision. But those are just measures. The important part of this paper is not the measurements. Okay, so how this goes. Like PageRank, I'm trying to define a score, but as opposed to PageRank, these are two scores. So both methods use two numbers. H of X is the hub score of page X. X is like before the page. And A of X is an authority. Am I spelling this correctly? Authority. Authority score of page X. But we don't have one score, we have two scores. Now, what's the concept of a hub? Why is it a hub, a high score? So let's make a little table, H, that's hub, and A, which is authority, and then this is high versus low. So what makes a hub score high? This is common sense English, not mathematical. What do we mean a good hub, high score hub? Why is hub? I'm not talking about links. Where would you tell your friends, hey, that's a good hub page? What would that mean?
Has many links.
It's a good place to have your search on, right? If you start on that page, you quickly get to answers, right? So it's a page with many good links. It doesn't mean the answer you're looking for is on that page necessarily, but it means that if you hop in there, from there you can find all the information you want. What would be an authority that have high score? Okay, but what authority means? I mean, many pages provide answers. Good answers. But good is a general term. I'm looking for something more specific than good. Accurate.
Relevant.
I'm looking for another word.
Relevant.
Relevant and accurate and good is the same. I'm looking for more like authority. What authority stands for? Why would you say that's a high authority?
Prestigious.
Trust. Or prestige. I think in this sense they are similar. So trust has to do if I get different answers from different pages, which one do I believe more? Take politics these days. Everywhere you go, it's a different answer, right? Every single topic of the day in politics, you can go to 3 or 4 websites, you get an opinion about why that is. And they're very different opinions, right? So who do you trust? If you're leftist, you're gonna go with CNN. If you're rightist, you're gonna go to Fox News. That's fine, you know? But see, it comes down to trust, right? Actually, factually, if you look, I've discussed this with somebody, can you disprove either CNN or Fox News factually? Can you go and say, this person in that date said the following, and factually I can prove that is wrong? Very hard to do on both networks. Yet most people definitely prefer one to the other, right? I mean, if you look at how many people watches one at random between Fox and CNN, they're very few. So it's a matter mostly of trust, right? Of course, it has to do with the political inclination of the person, no doubt about it. I'm not inclined personally to CNN or Fox. I'm not politically biased here. I'm just saying this has to do much more with trust than with factual information, right? Okay, so that's what we want. But we want the recursive function we're gonna have, which is like Pagerank, it's gonna be a combination of hubs and authorities. So the difference between these two algorithms is how is a hub computed as a function of authorities, and how is an authority score computed as a function of hubs. Turns out, the people who invented this whole mechanism, hubs and authorities, it's due to hits. This guy is a very famous computer scientist. John Kleinberg at Cornell University is a huge name in algorithms. I mean, really big name. And he came up with the idea that says, in a hyperlink environment, like the web, from a user perspective, hubs and authorities present different qualities. One is an authority page that I can read there something and it's relevant, what I'm reading and I can trust it. That's the authority page. And the hub is the typical page where users go to find out information. If you happen to go to a particular Yahoo page as your hub, for example, many people set that up as their home page. When they open the browser, they see a hub. It means they like that hub because from that hub they can find out whatever is relevant for them. It could be news, could be the weather, could be locations, maps, whatever else, right? In fact, most of the internet now, most people navigate it to hubs. I mean, everybody who types a URL means to go to a hub. If you type facebook.com my page, that's a hub for all kinds of things. If you type Google Maps or Google News or something like that, that's a hub, right? If you have a financial service, you type, again. A lot of these services have repetitive information. Most of them offer news that are typically the same news. But people prefer certain hubs. Authorities have much more to do with trust, and I think it applies mostly when I have conflicting information or a lot of recall information. I'm looking for something and I get 30,000 relevant results. Okay, which one of these are the ones should I look for? Most people like Wikipedia as authority pages. Most people believe what's written in Wikipedia. So you would see, for example, that for what's called an open query, open queries are queries for which user doesn't know what to expect. I'm typing diabetes without knowing what is it. I just want to know about it. Most people would trust a Wikipedia page. In fact, even for politics, the example I gave earlier, most people, both left and right, will believe what's written on Wikipedia much more than what CNN or Fox News are saying. So Wikipedia somehow managed to be a reasonable authority for general public. It's also easier to read than other pages, which makes it, I think, desirable. So the person who came up with this mechanism, hubs and authorities, had the following critical statement that made actually this person, John Kleinberg, famous. Hubs are a function of authorities, and authorities are a function of hubs. There's a recursion going on here. The principle is very simple, of course, and I think you're going to find it obvious. What it's saying is, to be a good hub, you have to have links to good authorities. And to be a good authority, you have to have links from good hubs. It's still recursive because the notion of good, it's built into this functionality. It's the same like PageRank. To have a high PageRank, you have to be pointed out by pages with high PageRank. It's just split into two kinds of goodness. There is the goodness of trust, authority, and goodness of hubs close to information. So he devised a schema that said, this is how we should think of information on the web. Okay? So how does algorithms work? Hits. So actually both algorithms have init phase. Before we do this, so actually I'm going to do this, but before we do this, you have to accept there is a kitchen setup in here. You know, before we cooking, we need to set up our tools and stove and all that, right? That with food in the fridge. So there is a, how do I go from the query to a set of documents to do this, to run my algorithms on? To run either hits or salsa or topic sensitive PageRank. Topic sensitive PageRank. So we can call this a preparation step because it's not related to the algorithm, it's most related to, okay, how do I set up this whole thing with respect to a query to do this? So we're gonna end up with base set, I think it's called. Let's see. B of documents. So we're gonna have an init. Maybe I shouldn't do this. Too much detail for something that's not relevant right now. This is how it gets initialized the score. So X, it's a document in B. X belongs to B. This is the base set. And X is a page or a document. This one has a different initialization. I'm going to skip it for now. And then here's the loop. So that's hits. That's salsa. The loop says for each X. You see, this is U and V. We have two different names. Let's see, for each X. we're going to update the authority score. So A prime of x is the sum of all the y's Okay, so if I want to measure the authority score, recompute the authority score given hub scores, I pick a page X, and I'm saying, I want to say the authority scores I'm computing is the sum of these hubs, but which hubs? Which pages should I look at? What's the relationship between authority and a hub? What did we say? A good hub points to a good authority. So which pages should I include if I want to measure the quality of X as an authority? Who points to who here? So Y has to point to X, right? And if I want to measure the quality of X as a hub, given authorities, who has to point to who here? X to Y. So this is all the pages that point to X, and this is all the pages that X points to. I think the paper does it better than me. They use this notion for each Y, use all the X, A of X, to make consistent notation, and this is, I'm updating the all Y's. It's the same mathematically as before, but then clearly here we have what? Who points to who? Always X points to Y. Is that right? I got it backwards. X hub points to this, and this is the hub. Y points to X. Of course, I can't just do this. I have to, those scores will go to plus infinity this way. I have to renormalize them. So I have to say H is now H prime divided by the norm of H prime, and A as a vector is the A prime now divided by the norm of A prime. So by dividing the norm means the norm of these things will always be 1. Right? So I'm replacing the old hubs with the new computed scores normalized in such a way that their norm is 1. And I'm replacing the old authority scores with the new authority scores, but normalized such that their norm is 1. So this is a process that's going to be repeated, loop, this whole thing, until there's a convergence criteria, until something happens. How about in salsa? There's the init phase. Well, I'm going to skip it. I'm going to show it to you on the projector. I'm not sure. I'm guessing that it's the same like Pagerank. We want to stabilize those scores. So when hubs don't change much and authorities don't change much, we call them convergent. Euclidean norms, when we normalize the Euclidean norms, I think it makes convergence a little harder. As in, there's more points in the space where the things could go. That's my, I'm speaking now not about hits, but in general. If values get divided by Euclidean norms, What does it mean geometrically? It means after I divide by Euclidean norms, it means that it's on a circle. All these vectors are on a circle effectively. And I think there's quite a lot of positions that are possible. I'm not sure how long this takes to converge. My guess is that this will take longer than Pagerank. So here's what we're gonna do here. This is a little bit more complicated. H prime of U, that's a new score of X, sorry, or what did you say? Halves are for Y. H prime of Y is a sum, two sums. We need a little drawing here. To understand where this is coming from. So I have a Y here. And it points to something, say X, and something else, it also points to X. Let's say Z. So now I'm trying to update the half score of Y. How good is Y? It's the half score of I want to make sure I got this right. Let's say Z points here. So let's see. What is this saying? The half score of Y check it. Okay, so we get it right. What is it saying? What makes Y a good half? It points to good authorities, right? Like X. So this is a hub, and this is a hub, and this is an authority. So to make Y equality as a hub, it has to do with X being good authorities. So this is saying, look over all the Z's that point to V. X, sorry, and Y's that point to X. So this is a double sum. This is look first for all X's that Y points at. That discovers the authorities. And then look over all the Z's that Z points to the same X. Why do I need the H of Z has to do with how good is Z as a hub, right? What it has to do with in degree of X? Why do I divide here with the in degree of x? This is our degree of z. So why do I divide with the degree of x? The more arrows are into x, the more the quality of x has to be divided to more hubs. So the less arrows I have in degree of x, the more the quality of x can be related more to the hub y and z. Why do I divide with the our degree of z? Z points to things too, right? My information about quality of x comes from z as a hub. So the more z distributes to other authorities, the more impact, the less impact it has on one in particular of x. So if you are to distribute quality of z as a hub to all the authorities, how much of that goes to s? Assuming uniformity, this is the our degree of z. So that's why I divide this here. So let's try to parse this formula again. My problem is updating y as a hub. So I go through all these x's. This is just one of them, but there's another x and maybe another x, another x. Now how do I measure this, this x quality? I'm looking at all other hubs around, and I'm saying, I distribute that value as a hub. I see how much goes to x. So that's why I have to divide with how much of z goes to x, that's our degree of z, and how many other links are to x, that's in degree of x. Once we understand this, the other one is similar. A prime, the new authority score for x is the sum over all the y's that point to x, and the sum over all the z's that y points to them. And that will be the score of that authority z divided by our degree of y times in degree of z. So let's draw that picture. I have an authority x. I'm looking for hubs that point to it. So one of these hubs is y. So I'm looking for all the hubs that point to it. This is authority, this is hub. But I'm looking now at all other things that y points to. There's this z right here that also have other links to it. So how do I measure the quality of this x? I'm summing up over all the hubs that point to x. How do I know this is a good hub? Because it points to other good authorities. So it's the quality of authority. It's the same principle like in here. It's the quality of this authority z. I have to divide by how many links coming out of y. Because if there's many links coming out of y, then the contribution of y is diminished. The how much is y to z, it's 1 over how many links y has. And then in degree of z has to do with, even if d is a high authority, in order to transfer that quality to y, I'm depending on how many other links are in Z. If there's many links, I can only transfer a little bit. So why set it up this way? This is a way to address hubs as a function of hubs and authorities as a function of authorities, as opposed to this in here, which is a recursive between hubs and authorities. I have to update authorities as function hubs and hubs as a function of authorities. Right? So does it work? Okay, so assuming we do this, what do we get? I want to put that paper up and we can talk about it, including how is the query going to lead to a set of docs for which I do this, right? There's a process that's not being used in a lot of crawling and measuring PageRank. I get the query, I create what's called a root set first. That's a basic set of relevant documents. And people even annotate those documents. You can think about it this way. Query goes to a root set, which goes further into a root set and a base set. The root set is primarily based on relevance, documents that have the right keywords. The base set is primarily based on outgoing links from the root set. Where else can I go quickly? What are the pointers, the web links that could be linked to other documents? And you can set up the sizes. How much is the root set? How much is the base set? This process is used in, it's been related to this HITS paper, but I think it's been used now in many other problems. First, look at the relevance, create a set of documents that's relevant, and then expand from there based on BFS links. Okay. Let's look at this paper. HITS and salsa, those are the two algorithms. So I want to go through the paper, like, understand not just the result, but how they set it up. So first of all, what is HITS, what is salsa? They talk a little bit about measurements. The one that you're familiar with now should be mapped, as in not the computation, but you've seen this number in TrackEval. The number over all the queries is mean average precision map. By next week, we're going to know all these measures, NDCG. NDCG is used a lot by Microsoft. It's their creation, came out of Microsoft. And mean reciprocal rank is a particular one that just ranks one object in a list, right? But by now, there are many, many metrics of information that we go. So what do we want to do? First of all, in an academic paper, we describe a little bit of the problem, fundamental problems, rankings of results, and then how people think of this hyperlink environment, how to measure importance in hyperlink, right? Of course, PageRank came first, I think, in mind, and then HITS, and then salsa. How do we set this up? So I think in the abstract they mentioned this a little bit, maybe not. I think those people here crawl something. So, breadth first search web crawl, they retrieved 463 million pages. And I think they've seen 2.9 billion URLs, links between those. That's a pretty big crawl. I wonder if they did it or they used somebody who crawled this thing. This paper is from 2007. This is right there, Sycamore 7. Sycamore is a prestigious conference for information retrieval. Not the most prestigious, but quite a popular one. It has 3 sections, this conference. Information retrieval, knowledge management, and I think databases. And it's a huge conference. It's the kind of conference that there's a few thousand people going to, big event. And in 2007, I think, to crawl that many documents was not easy. I don't think it was an easy thing to crawl 463 million pages in 2007. Now, it's not that hard, but back then, it was remarkable, I think. And then we have 28,000 queries from live search. This might have been Microsoft or paper related to Microsoft research. I think, isn't that live was Microsoft before now? Was it? The live, yeah. Okay, so there were some sampling. What you guys are gonna have to do for homework 5, once I see the results for a query page, I need to, at least for some of them, mark them as good or bad. We call it relevant, non-relevant. You can say yes or no, 0, 1. They have a grading of how many grades are here. Best, right, is definitive, excellent, good, fair, bad, and detrimental. This, I think, is a 6 scale. 0, 1, 2, 3, 4, 5. It's being shown by Microsoft primarily that if you tell people grades like 0, 1, 2, 3, 4, which now most services rate on a 5-star scale. I think in most places you put some allow half stars, but most of the ratings are 1 to 5. It's been shown that people's perception of these stars, it's exponential. In the sense of, if people rate a movie as a 4, it's twice as good as a movie they rate as a 3. If people rate a product on Amazon as a 5, it's twice as good as a product they rate as a 4, which is twice as good as a product they rate as a 3. So the natural, by experiment, by trial and error, they're showing that if there is a grading scale, it doesn't matter the grades. People ignore the grades, excellent, good, fair. Nobody knows what fair means. What is fair? I mean, what people understand is fair is better than bad and less than good. But nobody, no human can quantify fair. You want to give it a try? What is fair as opposed to good and bad? I mean, how much better is a document? Suppose you type right now diabetes, and you get a bunch of results of diabetes, and I'm telling you, you have to mark each one of the results with one of these 6 things. How much more useful is a document that's fair compared to a document that's bad? Obviously, it has to be more useful. If both documents are equally junk, you wouldn't call one fair and one bad, right? So initially, when people thought of information retrieval, annotation, and judgments, they designed these very fancy schemas. Turns out nobody understood what fair means. So the problem with this is that I would say fair for a document that he would say good and she would say bad, because we have very different notion of what fair means. But while we would not agree on the exact names, we would agree on comparison between 2 documents. It turns out that people are very consistent in terms of ranking. If I rank a document A as fair and a document B as bad, most other people would rank that document A higher than document B, but perhaps with different grades. So this kind of schema works hand in hand with the NDCG measurement. MAP is a metric, we're going to study this next week, that works very well with binary. If I have yes or no, also much easier to annotate yes or no. Most people have an easy time deciding yes or no for documents, but a very hard time assigning those grades. Again, there are many user studies who show that there is no consistent notion of excellent. But this schema, this kind of schemas work much better with this matrix NDCG right here, which because was introduced by Microsoft and became popular in industry. Most big systems now, Amazon, Google, Microsoft, use that metric, NDCG, not MAP. And that metric works hand in hand with ratings that are like that. A scale from 1 to 6 or 1 to 5, that's clearly in order. People can understand detrimental is worse than bad, which is worse than fair. It's just very hard to quantify for documents on, say, diabetes. Is it a fair document or is it a good document? It's almost impossible for people to consistently make that distinction. Okay. So measure effectiveness, I'm going to skip this because this is what I'm going to talk about next week in class. But average precision is some formula like this, and mean reciprocal rank is some other formula, and discounted cumulative gain is a different formula. The only thing I want to point out here is this notion that I talked about. If you were to map those classes, detrimental, bad, fair, whatever, into numbers, 0, 1, 2, 3, 4, because by now nobody uses this scale because it has been shown to be terrible. When people ask you for ratings, they give you a star bar and say between 0 and 5, how many stars are here, right? All the ratings now are stars. This is how people map the stars into actual quality. How good is 5 stars? 2 to the 5, 32. How good is 4 stars? 2 to the 4, 16. Because we think people's stars have an exponential value. In order for any one of you to put a 5-star to a product, that's probably you use it twice as much or twice as hard, or you're willing to pay twice as much money than you would for a 4-star product. So that has been shown, and by now everybody approximates those stars that we see everywhere, whether it's movies, songs, products, in an exponential scale. So that exponential is right here. But again, that's not the point of this paper. Now, hits and salsa setup. Here's the setup of these algorithms. What we have is we put a query, we run some basic content system like BM25. All these papers are using BM25 as the content ranker. The one you implemented for homework 1, that's the typical ranker people use when they say, I want to match keywords and nothing else. Like just a basic ad hoc query search based on keywords. Effectively, everybody uses BM25 as the first set of results they get. For some reason, in the 40 years since it got invented or so, nobody could beat BM25 consistently on ad hoc keyword search. Just content, pure content, no links, no nothing, no menus, no hypertext, no titles, nothing. Just a bunch of text, how to match. So most of these initial results, I think, are BM25. And then that creates a base set that gives me top how many documents I want that I think are relevant, base set. That's the same thing like if I want to do relevance feedback, I have to go to the top of my list and say, I think those are good documents. If I'm a big company like Microsoft, I may actually go and annotate some of these to get real feedback, to not take the top 500 and say they're good, but rather go through them and mark the ones that are good. So now I have relevance feedback. So you can see those people were saying here in the setup, they've actually annotated so many results, right? I don't know where, somewhere here said they've been on human judges, right? Were rated. So if I judge 17.3 results per query and I have 28 queries, how many human judges how many documents are being judged there? That's quite a lot. This cannot be a simple academic group. no academic group will have the human power to annotate that many documents. And now they use Mechanical Turks. There's a service that you create an interface, you give them some task like annotate these documents with respect to nuclear bombs, and it's much cheaper than it used to be, but still, that's probably coming from a research group like Microsoft, who had a lot of money. Now they don't have that much money as they used to have in 2007. Microsoft started with Microsoft started with a very noble cause to have a research group that was set up like in academia. Google and Apple and Facebook didn't start that way with their research. They said, we want a research group who solves our problems, not random problems. Microsoft said, no, 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 we're a big company. We want to have a research group so people, famous researchers we hire can solve whatever problem they want. Turned out that that was not a very financial sound decision to have such a group. I mean, the Microsoft research produced amazing research in so many fields, some unrelated to Microsoft at all, because they hired network engineers and famous algorithm people, people who got amazing awards and all that, as opposed to Google, Facebook, and Apple, who only hired engineers or scientists who can solve their problems. So I don't know if you know, Apple did a lot of research and engineering, breakthrough engineering, into batteries, for example. Batteries. Because they needed better batteries, right? Because they made so many products that need batteries, so they solved particularly many batteries problems. There are not many published papers because they want to keep it as a patented solution and such. Microsoft had a lot of academic type of research, many good ideas, just not immediately effective for Microsoft products. So that's why they slowed down on the money they had to do all kinds of things. So I'm setting this up now with the root set and the base set. And I'm setting up three kind of problems here. What links I'm willing to consider in my set of documents. So the query is like a filter, what documents I'm looking at. It has, again, I'm doing probably root set is the relevant set, and then I'm expanding that root set based on outgoing links. If I see a layer 1 or layer 2 BFS wave 1 or wave 2 links from the root set going out, I'm going to include these pointed out documents as a base set. It's again a typical setup for how to set a relevant crawler. And in here, I'm saying, okay, now I have my base set. What links I'm willing to consider? So there's three data sets created, three graphs. One it says all links. One it says only the links that have different hosts. And another one, only the links that have different domains. What do they mean by different domains?
Sites.
What?
Different sites. Like
Sites like what? Which one is the domain in a URL? Wikipedia is not a domain, right? Is it? .org, .edu is the domain. My understanding of this paper is that the domain, it says here, I do not want the links from edu to edu, because it says I'm only considering the ones that have different domains. Different hosts means what? Wikipedia.org to wikipedia.org. The reason they have an explanation here about this, we want links, because it's topical, it's based on a query, we use links as voting mechanism, right? PageRank, Salsa, and Hits count an incoming link as a vote of confidence or importance. The more links you have from other good websites, the better. So it has been suggested that if we think links are voting of confidence or importance, it shouldn't come from the same domain or the same host. It's the same way you guys are asked, I don't know if you guys went through the green card process or promotion process, you are asked for reference letters, right? The first restriction on reference letters is, we don't want letters from your friends. Doesn't mean your friends are not important people. It's in the same domain or host or school, right? If I work here and I want to be promoted or get a prize or something, I could ask for letters from my colleagues at CCIS, right? They know me, they like me. Not everybody, but most people do. So they'll write nice things about me. The first thing they ask you for letters, whether it's a green card application or it's a promotion or a prize or an award or something, is I want to see letters from other parts of the world, or other people, or other, they do other things. I think that's the same idea as in here. To count as a vote of confidence, it's better to come from a different website, from a different domain. Not to mention that in a hyperlink is the farming problem, right? It's easy to create a bunch of links or at virgil.com/something, and I create all my pages in there and I link them up, and now I create a lot of confidence votes within the same domain, the same host. So I think that's the meaning here. Across the host or across the domains have more voting power. So what do we do with this? We create a base set. Neighborhood graph has the links. And then here's the two algorithms. Initialization, those are the formulas I show you on the board. Like how do we update? They all, like PageRank, repetitive. Like I have an initial set of hubs and authorities scores. I update my authorities, I update my hubs, and then I normalize them, and then I repeat. Update authorities, update hubs, normalize, repeat, 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 repeat. That's equivalent in PageRank of starting with pi 0 and multiplying with them, and again with them, and again with them, until I see convergence, until I see my pi distributions convergent. That's the same principle. Update, 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 until I reach a notion of equilibrium or convergence. So I have a question for you. Can I write these equations in a linear algebra form so I can solve them with, say, eigenvectors or some other linear algebra method, right? I look at those updates, and I clearly see how they work if I'm thinking of my pi's. From pi 1, I go to pi 2 to pi 3, but of course in these cases I don't have only one pi PageRank, I have two pi's, the hubs and the authority scores. And there is an update procedure. It's not multiplying with a matrix, it's doing this sum here. If I could write this up as a matrix linear algebra, maybe I could solve it this way. So if you're mathematically inclined, you can take on that problem. Can you solve this in closed form as opposed to iteration until convergence? Right? This is the method proposed here, is to iterate through this until they converge. Salsa algorithm. Salsa algorithm has initialization that's a little weird. So they define this special base of hubs, and I think there's a base on authorities. There are slightly different sets, is that right? Yeah. There's a base authority set and base hub set for the purpose of initialization. But then the formulas for initialization are those formulas that we described here. I wrote it in X, Y, Z. This is written in U, V, and W. But if you replace U with Y and W with Z and V with Y, you get the formula. The important thing in these formulas is to not to get the math how it checks out, but rather why do I use, so the important is this drawing here. If I want to update Y, what should I look for? I want to look for all pages pointed by Y as authorities, and then for all other hubs, those are the Z's that point to X. And then I have the quality of that Z, I have to divide with how many outgoing links are from this Z and how many incoming links are next. So I think ignoring the actual formula, why is this in degree of X the factor on the denominator? Because the more in degree I have, the less Z matters for my formula here. Okay. And then what do we do with it? So we put up some plots. How those plots work? What do we measure in a plot like this? There's an x-axis and a y-axis. Y-axis typically means some notion of performance, quality. In this case, it's NDCG at 10, means the NDCG metric measure at the top 10 ranks. It's a very popular measure because Google and Yahoo and Microsoft use it. And the top 10 results in web search are everything that matters. In terms of Google measuring quality of ads and incoming money and clicks and all that, it's all in the first 10, because that's the first page. The number of people who click on the second page is like less than 1%. So NDCG at 10, very popular measure in web search for anything, because 10 is the top 10 results that people see. And then here is how many links I'm sampling per result. That's the initial query result. If I look at so many documents, how many links I'm considering there. The more links, the more this performance is going to grow. And then, remember when we talk about 3 data sets? We say either consider all links, or consider only across host links, or across domain links. So you have 3 data sets. And this is how they, the more links I'm considering, the more performance I get. Of course, this stagnates after what? This is all hits. Hits is one of the algorithms. This is hits. So this is hits authority. Hits authority. This is a different metric. My recommendation for reading academic papers is to read them slightly different than they are written. I've learned that the hard way by being a reviewer for many conferences, and I have machine learning. When you try to figure out what the paper is about, what the main thing is, it's quite hard to read it in the way the people wrote it. I know many reviewers do that. So here's the thing. You want to first figure out the core of the paper and then deal with the details, right? You don't want to read the story as you read a novel. Okay, what happened next? Okay, who's going to know? This academic person, all that. You have to figure out what's the problem, why is it hard, why other people couldn't solve it, and what's the solution here. Once you know that, then you go to the details. Okay, how many links these people have? How many alternatives? What they compare with? Da, 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 da. What other papers are relevant for this paper? So in that sense, it's better to fix a metric, NDCG, say, and go to that metric and first understand how these things evolve. Because if you have in your mind 3 or 4 metrics at once, then it's not clear what the point is. So what are those plots here? How many plots do we have? 6 plots. There are 3 metrics, right? So you see it's NDCG, map, and something. So let's just focus on NDCG. That means we have 2 plots, right? Only, because we just focus on NDCG. And now, what's in those 2 plots? What's the difference between plots? Salsa versus hits, right? They all deal with authorities here. Is there another plot for hubs? Maybe we're looking at something. Apparently, those people only plot authority scores, not hub scores. But let's say that authority scores. So now we have 6. This would be a problem for me as a reviewer. I would say it was not clear to me in the beginning how to look at this paper, because there's 6 plots in here, but I need to compare them this way. It would be easier if I showed those 2 plots. Those are hits versus salsa, because that's the main point of this paper, to compare 2 algorithms, right, for authority scores. So now let's look at those 2 plots. What is it that we can see in here? Are they different or the same? Why are they different? So those are 2 different algorithms, same metric, same data sets, like presumably the green line corresponds to that data set out IH, then the green line is also out IH. That has to be true. If you put a green line in a report that's different algorithms or different things, it becomes completely unreadable. So here's what I'm looking at. I say the blue lines are not that different in those two plots. So I would like to be able to ignore somehow this other thing, or not. Are those blue lines very different? So where this one starts? 0.08 something, this is 0.07 something. This is lower, but not that much lower. When this one ends? 0.12? This is 0.9, so this is lower than that, but it seems to me it has this kind of behavior that's similar to this one. How about the, say, the green line? This starts a lot higher, right, than this. And it doesn't seem to, it seems to be weird, like it goes up when the number of links are about, this is a logarithmic scale, right? Because 10 is not in the middle between 100 and 1. In a logarithm sense it is, but in a linear sense it's not. So it seems like around 9, 10 it's here, at 100 it's here, but overall there's not much variation. You know, we're looking at 0.14 something to 0.14 something, and it managed to get up to 0.50 something. I would say this one clearly tends to go up, but overall also not much variation. In the grand scheme of things, this is 0.408 something to 0.01. I would say the x-axis doesn't make much difference in here. It's pretty much, the number of links considered doesn't seem to affect either one of the scores a lot. But a significant difference is where this one starts. Even with few links, this starts much higher than this in terms of performance. So I know you guys are not reading as many papers as the PhD students, because you don't have to. But if you do, you have to set this goal first: problem, difficulty, solution. Read the paper for that only the first time. Try to understand, okay, you show me a comparison between two algorithms, what is it? The main thing. Once you understand the main core of the paper, that is the algorithm, what we did on the board, and the main result, then we can go over the details. Okay, they probably have an analysis section that they talk about how things are different when they're different. Let's see. I think they mentioned here somewhere that which line is all? All is the blue line, right? Yeah. They say, if we read this text here, the all version follows intuition. But the other ones, across hosts and across the domains, seem to have a different kind of behavior. And I think that was kind of my reaction when I see those +2. The blue line, that's all, seems to be consistent, but the ID and IH seems to be slightly different. And then I think we can go into this details of, okay, why that is. So I've read this paper at some point, and honestly, I feel like this is a weak part of the paper. It's not clear to me after reading this. I didn't read it today, but I read it before. Why is this IH, remember IH, across hosts only, and ID across domains only? Why is it that this reacts so differently? I mean, the two algorithms run on the same data sets. If I remove the intra-host links, I remove it from both salsa and hits. Why is it that I get different behavior? I didn't think this is a satisfactory explanation here. And I think, let me see, there's another plot here. This plot. What is this? So performance is the same, and this is G at 10. what is salsa out ID 3 versus hits out ID 9 or ID 100. So what is this number here? 15, 100, so on and so forth. I guess it's the number of backlinks that's on the x-axis. So how many? How many of those backlinks are considered? But there's no, in here I'm lost, I got lost into where are the hubs? Are those hub scores? I think, let me see. See, some of them are hub scores. The plots that we've seen before were only authority scores performance. So I think the plot before had to do with hits authority at 100. We saw that in the plot. That was one of the lines in the plot. That was the blue line. But then I'm including here hubs. This number, I could put it in the previous plot. If I go at 100 and I put the hub in there, hub line, I get another line in there. I'm also seeing Pagerank in here, which I didn't see in those plots. So I think the point is, let's pick a measure again. We don't want to go over 3 plots. Let's do NDCG at 10. That's pretty much the performances Microsoft measures it on the first page. What is the conclusion from this plot? What can we conclude by looking at this plot? Where random is when you guys come back and say 0.03 performance. And I say, that's random. Because I know if I sort the documents in random order, map is about 0.03 for the AP89 data set. So that's here. So then in terms of performance of relevance, including these annotations, BM25 is not beatable by those things. But that makes sense because those queries are based on keyword searches, and then BM25 in factual keywords, things like nuclear bomb, will be much better at producing relevant results than anything based on query with authorities and hubs, right? The problem is, even if I start with a good base set, once I go without links, there's no guarantee that I'm going to have nuclear bombs in those other pages, right? And then I'm sorting by hubs and authority scores. Those are primarily based on the link structure. If my query is primarily based on keywords like nuclear and bomb, BM25 will have a much better time. Authorities are also make sense to be higher up situated, right? Because in terms of what's relevant, an authority is much more likely to contain relevant information than a hub. So that's why I think the authorities are pushed towards higher scores. So you can take a look at some of this. This I feel like this is a paper that if you have time, it's not hard to read and debug. Your homework 4 asks you for some implementation salsa or hits. I think one is required and one might be extra credit. Okay. That's it. We have to decide what to do Monday in the following sense. Monday, I would start evaluation, those metrics, but I'm afraid that you guys are too far behind with the assignments. So I'm wondering if, since everybody is going to be at homework 4 dealing with the Webgraph, if it makes sense to have Monday a class about a new topic, or to rather do something related with the Webgraph and salsa and hits, whatever you guys need. So I have to decide that by Monday. Again, I said this last time, I don't want to completely disconnect the lectures with the assignments. And I have a feeling nobody will finish homework 4 by Monday. Yeah. Homework 3 is due when?
Tomorrow.
Tomorrow, and homework 4 is Tuesday, no? Or when?
Monday.
Monday. So that's what I'm asking. Are you guys gonna finish homework 4 by Monday? No? No? But when? Wednesday? You're gonna finish homework 4 on Wednesday? Homework 4 is not hard to implement in terms of algorithms. Once you get those web graphs, it's not that tedious. It's usually less time. 3 is tedious. So maybe we delay by a day out. We'll still have a lecture, of course, on Monday. But since you guys are going to be on this Webgraph, I don't think I want to jump on a different topic in the middle. I'll wait by Wednesday maybe to start.